Hello everyone, welcome to our SIG collab meeting, which is SIGPwny x SIGArch. Today we'll be talking about CPU security. I'm here on behalf of SIGPwny and Prathi is here on behalf of SIGArch. I'm Shweta, for those of you who don't know me in SIGPwny. I'm an admin and also an embedded lead here. You probably haven't seen me at much of the general meetings, but I'm one of the leads for embedded, so all things embedded, you can come talk to me about if you would like. I'll turn it over to Prathi. He'll introduce himself and tell you guys a little bit about SIGArch.
Hello everyone, I'm Prathi. I'm on behalf of SIGArch. We're a computer organization RSO. We're based in the ECB. We have our general meetings every Wednesday from 5 to 6. We teach like RTL, like computer organization design. Basically, we teach everything that the class CS 411, not CS, ECE 411 and CS 422, I think, teaches. 433, and like 233, the precursor. Yeah, that's about it. We can just get started. You guys can join the Discord.
As usual, all of our meeting content can be found on sigpwny.com/meetings if you guys would like to follow along on your own devices. So at this meeting, we're going to start off with telling you what a CPU is, and then going over some CPU optimization techniques, and then some vulnerabilities that come as a result of these optimizations. And then at the end of the meeting, we're going to have a little hands-on experiment from which you'll find the meeting flag as a result of the experiment.
Yeah, so what is a CPU? A CPU is essentially just you can think about it as like a hardware FSM. All it does is it takes in data, processes it, and spits it out. It interfaces with memory because we need some way to store the data we process, and yeah, that's about it. So a CPU can be broadly like broken down into 5 different stages. Like this is a basic overall structure of a CPU. The fetch stage just like as it mentioned, fetches instructions from memory. The decode stage kind of breaks it down into smaller micro ops and decodes it so that it can be executed. There's like various execution units, especially nowadays with modern CPUs. We have floating point, we have vector, we have yeah, we have like a bunch of other stuff. And the main execution unit is the ALU. It does like basically add, subtract, XOR, any logical operation, etc. And we have another stage for interfacing with memory because that takes indeterminate amount of time. And then we have write back. So the write back stage actually changes the state of the CPU by actually modifying the register file, which is an internal set of registers that the CPU has access to.
So as Prathi just went over, the main job of the CPU is to execute and fetch instructions. So one of the techniques that's used to optimize CPU performance is pipelining. So as he said, instruction execution is broken down into 5 stages: fetch, decode, execute, memory, and write back. Through pipelining, a CPU works on multiple instructions simultaneously. So it's not going to execute one full instruction and then another full instruction. It's going to parallelly execute multiple instructions at the same time. So we'll have a diagram on the next slide that kind of breaks this down. But basically, it starts the next instruction as soon as the previous one moves on to the next stage. So for example, we have instruction A and instruction B. Once instruction A goes in from the fetch stage to the decode stage, that's when instruction B is going to start its fetch stage. So what this does, like I said before, it's going to reduce the number of clock cycles required to run the same set of instructions. So for example, right, we have 5 different instructions. If we were to execute them all consecutively, if we decided to execute one instruction fully and then the next instruction fully, that would take 25 clock cycles to execute. But because of pipelining, we can execute all 5 instructions in only 9 or 10 clock cycles total. And then another facet of this, when we have pipelining, we also need branch prediction, because when we have instructions, generally what happens is our PC or our program counter is going to increment sequentially. But when we have a branch instruction, for example, in assembly, you guys are probably familiar with this if you know how assembly works. the PC is going to jump to a non-consecutive value if we branch. So, for example, if we have PC at offset 0001, it would usually increment to 0002. But if we have a branch, for example, it could go from 0001 to 0005, for example. Branching is always based on conditions, but conditions take time to execute, and we want to optimize CPU performance. So what the CPU is going to do is going to predict which branch is going to be taken based on historical patterns. So this can be taken from a branch history table, for example. So the CPU has a branch predictor in it that basically learns from the history of the different instructions that have been executed to see what the general trend is. If there's one instruction that happens, what's the next instruction that's going to happen historically based on that? So the CPU speculatively executes instructions based on the predicted path that it takes up. Once the branch condition is actually evaluated, the prediction is validated afterwards. So say the CPU predicts that instruction A is going to lead to instruction B. Once the actual instruction A has been fully executed, we're going to actually see if that prediction was correct. And most industry standard CPUs have 95% or higher prediction accuracy. So because of this branch prediction technique, there's a vulnerability that's introduced, which is called Spectre. Spectre was originally discovered in 2017, but it was publicly disclosed in 2018. And the paper that's relevant to it is linked at the bottom of the slide if you guys want to read along. But this paper was published in January of 2018. So what Spectre does is it exploits branch prediction to make the CPU speculatively execute malicious code paths. And then the origin of the name Spectre comes from speculative execution. And if you guys want to look more into this, the official MITRE references are given below. How it works in depth is that the attacker repeatedly runs certain instructions to train the branch predictor, which triggers misprediction. So if, say, we want to execute a certain memory access, we could train the CPU to think that every memory access is correct, and then we could have it when we actually want to access certain memory that isn't supposed to be accessed, we can have the branch predictor mispredict and go to a certain memory location that we want it to go to. So we'll outline an example in the next slide, but the general idea is that we can train the branch predictor to do things that we want it to do when it shouldn't be doing that. So during a misprediction, basically the CPU speculatively executes malicious instructions, like I said, and this is usually used to access forbidden memory or memory that generally should not be accessed. Though the speculative work gets discarded once the actual check happens, there are traces of the data or sensitive or secret data in the CPU cache. And attackers can then use side channel attacks to actually access that information that's in the cache. So to break this down into more detail, say we have this if statement, right? So we have this check as to whether x is less than array1 size, and then we assign y equals array, and then the index is going to be that array1 x with the x index times 4 kilobytes basically. And how we use this, for example, to execute an actual Spectre attack is that we would repeatedly call this chunk of code with valid balance of x. So for example, we would repeatedly call this chunk of code with valid values of x, such that x is always less than array1 size. And this is going to train our branch predictor to think that the condition is always going to be true. So when the branch predictor is actually run on our malicious value of x, it's still going to execute the next the actual instruction, that y equals statement, even if x is not actually less than array1 size. So for example, when we actually want to execute this entire attack, once we've repeatedly called this chunk of code on an actual correct value of x, we flush the cache. This is going to be important all the way at the end of the attack, but once we repeatedly call all of the chunks of code to train the branch predictor, then we're going to provide the malicious value of x. So a value of x, for example, that's not less than array1 size and access a memory location that has vulnerable or sensitive information that we want. Once the if statement is actually evaluated with that wrong value of x, the CPU is going to speculatively execute the array access so that y equals array2 index array1 x with our malicious value of x. And now that y value is going to be in the cache since it's been speculatively executed. Once the branch predictor once the CPU figures out that this condition, that if condition, once it catches up and figures out that that condition is actually not true, all of that speculative execution is essentially going to get thrown out. But we have the y value in the cache still. So what we can do is still access via side channel attacks the values from the cache. So for example, we would see which memory access is the fastest because it's in the cache, therefore it's going to take the least amount of time to access. And we know that whatever value or whichever memory page takes the least amount of time to access, that's going to contain our secret or sensitive data. Okay, the next optimization technique that CPUs use that can be exploited is out of order execution. And this is when CPUs execute instructions in a different order than they appear in the program. This reduces performance penalties by eliminating false dependencies between nearby instructions. So here's an example of out of order execution. Say we have these 4 instructions that the CPU needs to execute. We can see that the first instruction is going to take 200 clock cycles to execute. So we don't want to do that first because we want to optimize their performance, right? So we can see that instruction 2 doesn't really have a dependency on instruction 1 because we're just adding a value to register B and instruction 1 only deals with register A. So what's going to happen is that we can execute instructions 2 and 3 while instruction 1 is happening since there's no actual dependency between them. So the vulnerability that comes as a result of this is known as meltdown. This was also discovered in 2017 and publicly disclosed in 2018, which is why if any of you kind of followed the news with Intel and things like that, Meltdown and Spectre kind of came out at the same time. So that's why they're kind of paired together in news in general. So Meltdown exploits out-of-order execution to read kernel memory from the user space, which we don't want. And this primarily affected Intel CPUs. The origin of the name comes from melting down security boundaries, and we've given the official MITRE reference there. So how Meltdown works specifically is that the attacker has an instruction that tries to read from kernel memory, and this instruction is supposed to cause an exception, but since we have out-of-order execution, the CPU is going to execute the memory access before the permission check completes. So we're not going to have the exception caused because the actual memory access gets executed before the check even finishes. But once the permission check is complete, like kind of as a parallel to branch prediction, if we find out that this permission check completes and then we weren't supposed to have that memory access, the work from the out of order execution is discarded. But again, we still have those traces in the cache that we can get from our side channel attack.
So yeah, most of the attacks discussed today were due to like speculative execution. This attack is no different. It uses a concept known as prefetching, which is I'm sorry. Yeah. Yeah, what's
So the previous 2 attacks are focused on mainly, even though we may be executing code that isn't actually going to be used, that code that's being executed will fill a cache with information that we can access.
correct. Yes. Oh.
And then after we're using like rob attacks or side channel attacks, we can get that information from the cache, is our main.
Okay, thanks.
So yeah, side channel attacks is essentially just like reading the cache when you're not supposed to. Like you're technically not supposed to have access to like the CPU cache, but you can just like read it out based on like some debug pins that they put in the CPU. This is also very similar. So this attack is go fetch. It's a pretty recent vulnerability found in the M1, M2, and M3 Mac devices. It's based on the DMP prefetcher found in the M1, M2, and M3 Macs. So essentially, prefetching as a concept is very similar to branch prediction, except for memory access patterns. So prefetching essentially just like gathers a bunch of data, puts it into a cache so that the CPU doesn't have to go all the way down to main memory to fetch data it potentially wants to use in the future. A very common usage of prefetching is essentially when you have an array. Let's say you want to fetch all the elements of the array, put it into your cache, and then you don't have to go all the way down to main memory to actually fetch the other elements of your array. Because you know, once you access one part of the array, you usually access the other parts of the array as well. So the DMP prefetcher specifically is a pointer chasing prefetcher. So it essentially looks for instructions in assembly that kind of look like pointers. So since pointers are stored in a separate part of memory, pointers essentially look very similar. They have like the leading bits be roughly the same. So how GoFetch exploits this is by feeding malicious code, writing malicious code that has like pointer-like attributes or pointer-like attributes so that the CPU actually reads from these pointers and actually executes your code instead of the intended code. So the word like the vulnerability GoFetch comes from the fact that you can essentially extract the encryption keys from like M1, M2, M3 max using this vulnerability. You can find out more about this on their actual website, gofetch.fail. I'm sorry, I forgot to link that, but yeah. And then due to this being a hardware construct, it's like really difficult to turn off. You can actually turn this off in. I'm sorry. Is all good? Yeah. So due to this being a hardware construct, it's like incredibly difficult to turn off. So they found ways to turn this off for M2 and M3 max by turning off like a specific bit that actually turns on and off this DMP pointer chasing prefetcher. But on M1 max, it actually can't be turned off even with like firmware updates. So it's probably like pretty bad. And on the previous Intel-based Macs, there was another bit you could use to turn off the DMP pointer chasing prefetcher as well. So yeah. Any questions?
So you're saying that the M1 Mac basically made this like permanent like vulnerability sort of way?
Yeah, it's essentially like really hard to fix. So what programmers have to do is essentially like not write programs that essentially use this prefetching optimization. So your programs are going to be very slow now, but at the cost of them being safe. So you can turn this off. It's like an additional feature you can enable, even on M1 Max. But on M1 Max, it's slightly harder to write code to prevent you exploiting the DMP. Essentially. Yeah.
They figured this out by reverse engineering Apple's.
Yeah, they reverse engineered Apple's DMP implementation. This was actually discovered before by another group. I forget their name, but they couldn't prove that it was like useful enough to actually be a vulnerability. So the GoFetch team actually proved that you could extract the RSA keys from the CPU using this method.
Like how did they actually reverse engineer the hardware? Like how are you?
Oh yeah, so if you have like a specific like memory access patterns, you can essentially track this you can track what goes into the cache essentially because you have access to the RAM and you have access to the CPU. So you can tap into the bus that goes in between the RAM and CPU and you can see what data goes in and out of RAM, right? So when you see the data that goes in and out of RAM, you can like kind of model this pattern as like access pattern. And then you can actually feed in certain patterns to actually enable like your specific version of what data goes in.
It's kind of by like black box.
Yeah, it's kind of like a black box and you're just like kind of tapping into the bus in between them. Yeah. What's
Right, what do you mean by tapping in the bus? Like,
So
I know like the, I'm just saying shit for like a system on shit.
yeah, it's an SoC, but they still have like external memory, right? They still have like DDR5. That's not like part of the SoC. They still have like storage or like not necessarily RAM, but like storage. The storage that's still off chip technically. You can still tap into that bus there. This is mostly a vulnerability because of the fact that prefetching can be turned on and off on the newer series and it can't be done in the older M1 series. So that was just a minor oversight. Yeah. So we can probably go towards the activity.